So we have started the qualitative description. Some introduction I have given in the previous class, PN junction section. So today we will continue with what are the various descriptive parameters to qualitatively describe the current flow at the junction. So as an introduction, we have taken what is the basic structure at the PN junction. So we have a neutral P region, neutral N region, as well as a space charge region in between these two, and the width of the space charge region is taken as W, and it is also known as the transition region, and the built-in potential is designated as V naught, as well as the electric field, it is E. So these are the notations used throughout this particular module. Okay. And at equilibrium, whatever the potential that is built up inside the junction, that is called as a built-in potential. So that this is a diagram which shows what is the equilibrium conditions at the junctions. So I think in the previous sessions we have uh, discussed about all these things. So when individually we consider the p-type material and n-type material, so these are the bands. So you can see that the Fermi level close to the EV in case of p-type material, and Fermi level it is closer to EC in case of n-type material. So whenever the junction is formed by joining the p-type material and n-type material, so then a space charge region of width W is formed, and the direction of electric field is from N to P. And because of this, whatever the electrostatic potential that is built up across the junction, so this is indicated as V naught. V naught. Okay. So for the individual p-type and n-type material, this is a band diagram. But for the PN junction, okay, the band diagram is as shown. So here ECP and EVP, so they are on the p-type material, and EFP. Okay, so EFP, it is a Fermi level towards the P region, and coming to the other side, N region, the naming is ECN, EFN, and EVN. So these are the three related with the N-type material. Okay. And here you can see that there is a transition of the amount Q into V naught, so that we will consider now as one of the qualitative description for the current. And so this was a picture to show you what is the formation of the depletion region. So you can just recall. So you have a P region, N region. So when they are attached, so the junction formation is like this. So there is a rearrangement here, and same on the P region also. And this particular region, which is depleted of movable carriers, it is called as a depletion region or space charge region. Space charge region, as shown in the picture here. Now in this picture, so how the built-in potential, where it exists across the junction, so everything is shown. Okay. So that V naught exists across this junction for a region equal to W. Okay. So then, now starting the qualitative description of the current flow at the junction. Now in this, even in the previous introduction also I had told you that, so whenever an external voltage V is applied across the junction, okay, so it is assumed that applied voltage V, it appears across the transition region rather than the P type and the N type regions. Okay, so that is, it is assumed that whatever the external potential is there, it will completely appear across that W or the space charge region only. Okay, so and that applied voltage V is considered as positive. Okay, so whenever the external bias is positive on the P side and negative on the N side, and that we call it as a biasing voltage. So therefore, what is the result of this applied voltage? Okay, so this applied external voltage, its main effect is it changes the electrostatic potential barrier and also electric field within that space charge region. So now, because of this, there are various changes and various changes in the components of the current also across the junction. So therefore, what are the parameters that are affected because of the application of this particular bias? So they are listed here. The first one is the electrostatic potential barrier at the junction. So because of that external biasing, what is going to change is the electrostatic potential barrier at the junction. So this is the first parameter. And also the second parameter will be the electric field. Okay, so within the transition region. And also because of the application of external bias, so whatever the width of the space charge region is there or transition region is there, that is also going to be affected. Similarly, the external bias is going to affect the separation of the energy bands also. So and finally, it has its effect on the diffusion current as well as drift current as well as the total current. Okay. So therefore, at equilibrium, we have everything in the standstill condition. But as soon as you apply the voltage V across the junction, so then these are the 7 parameters that are going to be affected. Okay. So now we will take one by one. What are their effects? So among that, the first one is the electrostatic potential barrier. Okay, at the junction. What happens to this? Now for this notation should be clear for you. So you just observe this particular picture. So here you can see that it is a first party, okay? PN junction, and this is the picture at equilibrium. That is P equal to 0, and this W as usual it indicates what, the width of the space charge region, and at equilibrium condition, so Vp, Vn, and V naught. So these are the various levels, and V naught is the built-in potential barrier we have. Okay, now this is open. So that is, it is in the equilibrium condition. It is not yet biased. Okay. So these are the initial condition you can assume. And coming to this energy band section. So we have ECP, EFP, EVP on the P side, and ECN, EFN, and EVN. They are lowered by an amount equal to Q into V naught. Q into V naught. And this V naught is same as this V naught. It is a built-in potential barrier. Now what this is a usual or very natural band structure at equilibrium condition. So now, because of the application of external bias, so how this condition is going to be affected? Okay. Therefore, that is studied under two conditions. One is forward biasing, the other one is the reverse bias. Now, just observe the notations here. For forward biasing, our V will be equal to Vf. V will be equal to Vf, and V will be equal to minus Vr for the reverse bias condition. So what is the nature of forward bias here? The P-type material is connected to positive, whereas N-type material is connected to negative. Similarly, for the Vr, as it is a reverse voltage, it is minus Vr. So P-type material connected to minus and N-type material connected to plus. Okay, and here we indicate the applied voltage as Vr, and it is indicated as a Vr. Okay. So now this is the first part, that is part A is the equilibrium conditions. Now come to this part B. So whenever forward bias is applied, okay, so when you switch on this, so then what and all are affected. So first you observe the potential difference here. Okay. So whatever the potential barrier that was built across the junction. So now by comparing with the equilibrium condition, we see that its magnitude is reduced. How much it is reduced? It is V naught minus Vf. Okay, it is reduced by an amount equal to V naught minus Vf. So this is what is the effect of applying a forward bias across the PN junction. So in general, you can say that okay, the barrier is reduced. Okay, earlier there was a lot of barrier because of this. Because of this, any movement of holes and electrons across the junction was prevented. Okay, but now because of the application of forward bias equal to VF, so this space charge region, okay, it is shrinking now. Okay, the width is reduced. You can observe from the picture, it is reduced, and also whatever the barrier built-in potential was there, that is also reduced in its magnitude. Now its value is only V naught minus VL. This is what is the effect. So similarly, come to this band diagram, energy bands. So what happens to these energy bands? So earlier the separation was Q into V naught. Okay, so Q into V naught. Now the energy bands, they will also shift and settle again, and you can see that it is split up into two parts, EFP, okay, and EFN, EFN. Okay, so their magnitude is also reduced here. Okay, so therefore this entire V naught part is now reduced by an amount VF. Q into, okay, so V naught minus VF. In the equilibrium condition, its value was simply V naught, built-in potential. Now built-in potential is reduced. So the reduction is shown by minus VF. Q into V naught minus VF. Okay, it means that your Fermi level on the N side has just come closer to the EC level of the P side. Okay, now because of this, okay, there is a diffusion of the majority carriers. There is a diffusion of the majority carriers. That's why we say that during forward bias, a forward current will flow. Okay, this is what is the reason. Inside the junction or across the junction, the barrier is reduced, the Fermi levels are changed. So because of this, there is a change in the amount of current that is flowing across the junction. This is what is the first. The second one is come to this reverse bias. So whenever across the junction you apply VR, that is connect positive to negative and N to plus, then the reverse operation is going to happen. Now compare this electrostatic potential with respect to the first one, that is equilibrium diagram. So here, now the separation is still more. Okay, the transition is still deeper, indicating that the barrier is still more. Okay, and its value is how much? V naught plus VR. Now earlier it was V naught minus. There was a reduction in the barrier. Now the barrier is enlarged. Okay, so and the same thing it is reflected in the space charge region width also. So here you can see that W is enlarged. Now in this the forward biasing condition, the W is it is shrinked. Okay, so therefore the main effect of the reverse bias is the reverse bias on the potential barrier is the total potential barrier will be increased in the size. Okay, so this is what is the first part. What is that? That is the electrostatic potential barrier at the junction. So during forward bias, its value is reduced. During reverse bias, it is enlarged. Okay. Then coming to the next, electric field within the transition region. Now, because of the application of VF and VR, what happens to electric field within the transition region? So now again we will refer to the same picture only. So the amount of electric field in case of what forward biasing is reduced. Okay, so under forward bias condition, this field decreases as the applied electric field opposes the built-in potential. But whereas in the reverse condition, the reverse bias condition, the field is still more increased because of the applied voltage. The field is still more increased. So that is evident from the arrow mark. So here you have the arrow mark. Okay, so it is less than the equilibrium condition. Now in the reverse bias condition, the length of the arrow mark is more than the equilibrium condition. Okay, so therefore the electric field it reduces in case of forward bias, it increases in case of reverse. Now coming to the transition region with W. So what happens to this W? Okay. So now all parameters are explained with respect to the common picture only. So you need not write separated diagrams. So at once you just draw the complete picture containing all the information and description about all the 7 points. Now observe the transition region bits. So during equilibrium condition, the width is like this, and during forward bias, the width is reduced, and during reverse bias, the width of the space charge region is further enlarged. Okay, so therefore, the meaning is the biasing, the external biasing, either plus VF or minus VR. So it has its direct impact on the transition region width. Then coming to the fourth point, that is the separation of energy bands. So this already I have explained. The energy bands also. So now you just observe. This is the equilibrium band Q into V naught times. Okay, the distance between or the separation between ECP and ECM. Okay, now this is reduced in case of forward biasing. Reduced. Okay, but in case of reverse biasing, it is still more deeper. Okay, so therefore it is enlarged Q into V naught plus VR. It is enhanced. Okay, so indicating that uh, the less flow of carriers or almost zero flow of majority carriers. Okay. So therefore, it is not only the what width of the space charge region. At the same time, the electric field also getting reduced and increased. At the same time, the energy band diagrams. Okay, coming to the energy band diagrams. So here also, the difference between the levels it is reduced and increased in case of reduced in case of forward biasing, and the separation is increased by an amount equal to VR in case of reverse bias conditions. Then the next one is the diffusion current. So now what happens to this diffusion current? Okay. Now the diffusion current is nothing but it is a current because of majority carriers. Okay, so the majority carriers are electrons on the n side and majority carriers are holes on the p side. So now this is evident from the this particular picture. So here you can see that p region majority are holes and in the n region majority are the electrons. So now the diffusion current is the one which is composed of these components. Okay, so therefore the majority carriers, okay, so overcome the potential barrier and they will diffuse across the junction. Do you understand? So the majority carriers, whatever are there, okay, so they will overcome the potential barrier. Overcome in the sense, so their strength is more. They are able to succeed. Okay, so they will overcome this barrier. Okay, and they will diffuse across the junction. Okay. So now under forward bias, okay, under forward bias condition, we know that from this particular picture that under the forward bias condition, this barrier is already lowered. It is reduced by an amount equal to V naught minus Vf. So therefore, now this is a favorable condition now. As barrier is reduced, okay, so the majority carriers can easily diffuse from P to N and from N to P region. Okay. So whereas in case of reverse bias condition, so what happens? The condition is opposite now. Okay, now the barrier is enlarged V naught plus VR so that no electron in the N side, no electron in the N side or no hole from the P side can diffuse. So therefore, the diffusion current is negligible or almost zero under reverse bias condition. So therefore, that's why we say that during forward bias, maximum current flow is there, and during reverse bias, there is no diffusion current. Current is zero, and device is switched off. So whereas in forward bias condition, so full majority carriers flow is there. That's why device is turned on. Okay, so this is responsible for turning on and turning off of the particular semiconductor device. Okay, so then the other parameter is the drift current. Okay, so this drift current, it is usually insensitive to the height of potential barrier. Okay, drift current is that part of the total current. Okay, so which doesn't respond or which is not related to height of the potential barrier. What is this height of the potential barrier? This is what V naught minus Vf, V naught plus Vr. So here height is reduced, here height is increased because of the reverse bias condition. Now, this drift current, it is independent of these two heights. Okay, what is the reason then? Okay. The reason is this drift current is limited by how often the carriers are swept down the barrier. Okay, so rather than how fast they are swept across the junction. or across the barrier. Okay, so for example, on the p side, okay, you consider on the p-type material. So in the p-type material, the electrons are the minority carriers. Similarly, every electron on the p side, so which diffuses into the transition region, so will be swept down, swept down the potential energy hill. So irrespective of whether that hill is large or the small. So in the coming to this drift current part, okay, so this particular drift current, okay, so it is limited by certain condition. What is that? So it mainly depends on how often the carriers are swept across the barrier, across the barrier. Okay, so that's why on the p side, where electrons are the minority carriers. Okay, so therefore every electron on the p side, uh, which is diffusing across the particular transition region. Okay, so it will be swept down the potential barrier here. Okay, so irrespective of whether its size is large or the small. And also this whatever electron drift current is there, so it does not depend always on so how fast this particular individual electron is swept from p material to n material, but rather it depends on so how many electrons are swept down the barrier uh, per second. Okay, so it mainly it depends on how many electrons are crossing them. So it doesn't depend on how fast it's being crossed. Okay? So therefore, that is the drift current. Therefore, the total coming to one more parameter. What is this total current? Okay. So now the total current crossing the junction. It is the sum of both diffusion as well as the drift currents. Therefore, the electrons and the hole diffusion currents uh, are both directed from P to N, and the drift currents are directed from N region to P regions. Okay. So, therefore, the total net current crossing the junction will be zero at the equilibrium condition. So, at equilibrium, of course, we know from this particular diagram. So, at equilibrium, this V itself is equal to 0. So there is no sweeping of carriers across the junction. Okay? And this can happen only when they are biased. Okay? So therefore the net current crossing the junction at equilibrium condition will be 0. Okay? So this is because as drift and diffusion components cancel each type of the. So under reverse bias condition, what happens? The diffusion current, they are completely negligible. It is because of the large potential values. So therefore, the summary is here. Whenever you forward bias, so you observe the diffusion current, but whereas the drift current magnitude is very small, and whereas under reverse bias condition, because of this increased separation between the potentials, so the diffusion current is almost equal to 0. Okay. So like this, all the parameters related to this PN junction, they are all affected in their magnitudes. So whenever uh, either a positive potential or a negative reverse potential is applied across the junctions. So the next topic is particularly concerned with the reverse bias. So because we say that what is the condition for reverse bias? We have the p-type material. Just observe the last picture here. So p-type material connected to negative, n-type connected to positive. So that is in the sense whenever you are increasing the barrier, that's all. So reverse bias here it means so whenever you are enlarging or enhancing the potential barrier between p-type material and the n-type material, whenever you are increasing the space charge region width, so then uh, that mode of operation it is known as a reverse bias. So where diffusion current we say that is almost equal to 0. Then going still more deeper into this reverse bias condition. So here in this particular picture, we have some notations. So this entire diagram, okay, it is concerned with uh, the minority carriers here. Okay. Now here you have the terminology like this: XP, XN. You just observe picture A. What is the picture A? It is showing uh, minority carrier distributions near the reverse bias junction. Okay, so it is minority carrier distribution where near the reverse biased junction. So first of all, this is the P part, this is the N part. Now in the P part, minority carriers are electrons. Okay. Now in the N part, the minority carriers are the holes. Okay. Now this picture is showing their distributions, their distribution. So now here this N x of P indicates this is the minority carriers electrons in the P region. This is P x of N indicates the minority carrier distribution in the N region. And this 0 points, so whatever vertical line we have, 0. So these are what? These are the edges of the space charge region on either side. What is the edge? See here, in this picture, so we have the edge in the dotted lines. Okay, so at the end of this P region, we have a dotted line. At the beginning of N region, again there is a dotted line. So these are the two edges. Now these two edges are represented here like this. Okay, so N XP axis, P XN axis. Okay, so you can imagine that this is the dotted line. So from where onwards our N region will begin, and this is the line where or edge. So where the P region is going to end. Okay. So therefore, these are the edges immediately present at the junction. So here we have what? The neutral regions are there. Okay, so far away from these edges, we have the neutral regions. So in the neutral regions, there are no such electrical activities. We are concerned only at the junctions. At the junction, what is the thing that is happening? Okay, so at the junction, how minority carrier distribution is happening. That's all. Okay. So therefore, the reverse bias condition is understood. Now, due to this applied reverse bias condition, okay, so what happens? The minority carrier concentration, you just listen to this, the minority carrier concentration at the edge of each transition region becomes essentially zero. Now, this is what is the first condition. Now, because of this applied reverse bias, okay, the minority carrier concentration. See now, where is the concentration here? Carrier concentration is indicated by NP and PN levels. NP. Okay, so first of all, you keep in mind that this is the P side. This is the P side. The P side has electrons as the minority carriers. This is the N side where it has P as the holes as the minority carriers. So now imagine that on the P side, okay, NP is the carrier concentration. NP is the minority carrier concentration. Now at the edge, under reverse bias, okay, at this edge, under reverse bias condition, the concentration, here you can see that the dotted lines are there. Gradually the curve is tending towards zero. Now this indicates that during the reverse bias, okay, the minority carrier concentration at the edges tends to zero. Similarly, come to this other side. What is that? N region. In the N region, assume that suppose Pn is the whole concentration. Okay, but at the edge you can see that. At the edge you can see that the concentration gradually coming to zero. But it is not zero on the other side. Here, what we have, this is the neutral region. We imagine that this part is a neutral region. So starting from the neutral region, as you approach the edge, so towards the edge, okay, the minority carrier concentration will become zero. So this is an important feature under reverse bias condition. Okay, so therefore this particular action is called as minority carrier extraction. Okay, so this is called as minority carrier extraction. Because earlier their levels was like this, shown to the dotted lines. Okay, but now as soon as the reverse bias is applied, okay, so the minority carriers will tend to cross this particular barrier. Okay, so because of that, at the edges their concentration is going to fall, and this is technically called as minority carrier extraction. So which is analogous to what carrier injection during the forward bias, during the forward bias. Okay. So this extraction, what is the reason? Okay, the extraction it occurs, it is because of the minority carriers at the edges, minority carriers present at the edges of the depletion regions are swept down the barrier at the junction. Okay, so to the other side. See now. To understand this particular sentence, we go to this picture, this diagram. So here what is happening? This picture shows how the junction is formed. So this is a space charge region. Okay. So now you can imagine, for just a minute, if it is possible to okay. Uh, so you have to just concentrate on this particular region. Okay. So at the edges, I think this picture will be better to understand. Depletion region is there. Okay. So whatever this shaded part is there, just concentrate on that, the shaded part. So this edge you can consider on the P region as XP naught, and this edge is the XL naught. Now at these edges, whatever the minority concentration is there, okay, so why they are concentrated? Because you are applying the reverse bias, because of the reverse bias. Okay, so the minority carriers which are collected at this edge, okay, so they have a tendency to completely cross this. Okay, of course their number is very few. That's why it is drifting. It is not a diffusion. Similarly, on the end region, okay, on the end region, whatever the minority carriers are collected along this particular border, they are highly influenced by the applied reverse bias. Okay, so there may be what minority carriers in the other region also, but the minority carrier concentration we are talking about, particularly the minority carrier concentration along these borders, they are the ones which are severely affected, and their concentration is going to fall. Okay, so that's why in this particular graph, okay, so this curve, okay, this curve approaching zero, it shows that at the edge, as we approach from neutral region towards the edge, the minority carrier concentration is going to fall. Same thing on the n side also. Same thing on the n side also. Okay, so now this process is known as the minority carrier extraction. Okay, so this extraction means the carrier, minority carrier concentration at the edges is swept down the barrier, swept down the barrier, and they are able to go to the other region. Okay, so uh, so now when the holes at xn naught, or at the particular edge, okay, so when the holes at this edge uh, are swept across the junction to the p side, Now, what is the P side? Left hand is the P side for us. This is the N side. Okay. So whenever the holes are swept across the junction to the P side, you just clearly understand this. Now, left part is the P region. The right part is the N region for us. Uh, so this is the P region and this is the N region. N region. Uh, Now, this is the edge. I am talking about this edge. So this is the edge of the P region, and this is the edge in the N region. N region. So uh, now, so when the holes are swept across the junction to the P side. So where are the holes here? So here are the holes. Okay. So when these holes are swept across the junction, okay, so towards the P side, because of the electric field E. So what happens? A gradient in the hole distribution exists. Okay? And the holes in the N region will try to diffuse towards the junction. Okay? So now, although this reverse saturation current, okay, so it occurs at the junction by the drift of carriers. So this current is fed from each side of the diffusion. So towards the particular junction. Now, the rate at which these carriers drift across this particular junction. Okay, so now this is also known as the reverse saturation current. Okay, so the rate at which the carriers drift across the junction is also called as reverse saturation current, and the amount of that reverse saturation current it depends on the rate at which holes are arriving at xn naught. So xn naught is nothing but edge in the n region, edge of the n region. So here you can just see that. See here xn. If I put 0 here, n equal to 0, it means it is the edge of the n region. Similarly, xp0 means it is the edge of the p region. Okay. So now the rate at which the carriers drift across this junction, or in other words, the amount of reverse saturation current. Okay, it directly depends on the rate at which the holes arrive at xn naught and electrons arrive at xp naught. So because the holes are the minority carriers on the n region, so the rate at which these holes can come towards n region. Okay, so that decides what is the reverse saturation. So in the figure B, okay, in the figure B, there is a variation of quasi-Fermi levels is shown. Because of this applied reverse bias voltage. Okay. So on the P side and the N side, so how the energy levels are going to be affected. So that is represented through this energy band diagrams. Okay. So here you have to highlight about the minority carrier extraction concept, and also under reverse bias condition exactly at the edges what is going to happen. Okay. Now on the energy level diagram also here you can see that Q into it is V naught plus VR. So the barrier is increased. So because of this there is a lot of change in the energy levels also. You can just compare this picture with the previous one. That is under equilibrium, how it is. See, so under equilibrium, this is what is the condition. The Cn, EFN, and EVN we have, but due to reverse bias, so you can see that the entirely the levels are replaced or they are repositioned like this. Okay, and totally this the region of the hill. Okay, so it is much more deeper compared to the either forward or the reverse. Okay. So now this is what is the important factors regarding the reverse bias in that the minority carrier extinction. So in the next session we will discuss about what is this reverse bias breakdown.